All right, now as far as I'm aware, this is the hardest freaking Navier-Stokes differential equation problem that exists that you can do by hand. But yeah, even this one is not too bad. The algebra for solving for the boundary conditions at the end gets a little messy, so I probably won't solve for them. I'll just say 2 equations, 2 unknowns, we're good. But let's see. Okay, so we've got, what do we have? We have a freaking channel. And dp dx equals g, so just a constant, times cosine of wt, omega t. And yeah, right off the bat, you can tell it's not going to be fun. So boundary conditions, u at y equals 0. Oh, gotta draw the axis. X, y. U at y equals 0 for no slip, and u at y equals h equals 0 also for no slip. And I don't even have to draw it at this point, but that's h, the height of the tube. Or of the, I don't want to say tube because that means radial coordinates, and we're not doing that yet. Okay. Assumptions. 2D w equals du dx equals du dv d. What am I doing? My brain is getting fried again. Du dz equals dv dz. There we go. We'll assume dp dz also equals 0. That's the first assumption. Second assumption is, again, fully developed. This tube is infinitely long. So whatever's going on here is the same thing that's going on there, is the same thing that's going on over there. Which means that between them, there's no slope. So fully developed in x, and that means du dx equals dv dx equals dw dx, which equals 0. Cool. Yeah. Okay. We are cooking now. Frankly, the reason why I'm doing these, making all these videos right now, is because it's an excuse for me to study for my exam in a week. Okay. So now, I think we can do continuity. Du dx plus dv dy plus dw dz equals 0. Fully developed 2D. Okay. dv dy equals 0. V equals a constant that I'll call A. V at y equals 0 because you can't go freaking through. You can't come out of a wall because it's a wall. And V at y equals h equals 0. Plug in whichever one of those we want. Vy equals 0 equals 0, which equals a. A equals 0. Oh. V equals 0. Cool. I'm not going to do the pressure. I'm not going to do Navier-Stokes in the y, because all you do is extract part, like the y component of the pressure equation, and like I don't care. It's going to be similar to the last video anyways. Okay. So let's just go to Navier-Stokes and X. Is that right? Navier-Stokes in the X. Yep. X. Cool. Okay, that looks right. So what can we do? Let's get our assumptions out of the way. Steady state. V. That's too many lines. I want to be able to see the thing. V equals 0. Fully developed 2D. No gravity in that direction. We have a dp dx. Hold up. I did not assume steady state, which is the correct thing to not assume, because it is not steady state, because this varies with time. That's what makes it interesting. So we can't cross out that first term. We can with this fully developed 2D. I was saying, like, in my head, this is too easy, but no, we have to keep that, and that's why it's freaking difficult. Density du dt equals dp dx plus mu d squared u dy squared. Dang, it is raining a lot. I can see like 4 blocks away, and that's it. Dang. Okay. Well, a lot of stuff going on here. So, okay. I'm gonna write this out in a way that I like. Dp dx was g cosine wt. Would be g over mu, right? Yes. Yes. Okay. So we got some interesting stuff here on the left-hand side and on the right-hand side. So on the left-hand side, that's the homogeneous part. And yeah, so it's going to be u is a function, so UH for homogeneous is a function of y and t. And on the right side, we have that u particular is a function of just t, because there's just a t over there. And on the left side, we have a t and we have a y. Okay, let's do homogeneous first. Homog. And that means that you set the right side equal to 0. Very cool. So what do we assume? Last time we could assume that u equals e to the lambda t, or lambda y. But we can't this time because it also has to be a function of t. So what the frick do we do here? Well, there is a standard procedure for this type of stuff, and it uses Euler or Gauss, or maybe it's someone else, but it doesn't really matter. You assume the standard solution, because of course it's standard, Wt times a function of y. Don't know what that function of y is yet, but we will get there. So what you do now is you find all the derivatives that you need. So d squared, I wrote that u too high, I don't like it, over, let's start with the first derivative, du dy equals e I w t df dy. Yeah. And then second derivative, d squared u dy squared equals e I w t d squared f dy squared. That's pretty simple. So far, it is very simple. And then what else do we need? We need a du dt. So du dt equals iw, well, it's omega, but I'm calling it w, e to the iwt times f of y. Because you take the derivative, bring those two down to the front, and call it a day. Okay, now let's plug this stuff in. So we have e I, let's zoom in a bit more, wt d squared f dy squared minus ou dt iw e iwt f of y. No, it's not in the exponent. I don't want to write it so it looks like that. Equals 0. Does that look right so far? That does look right so far. So now what we do is, now we can do the same thing that we did last problem. We assume f of y equals e to the lambda y. Right? I'm looking at my notes when I say right. Yes, it is right, and of course it is, because I am always right. So we plug this stuff in, well, I'll write out the derivatives. d f dy equals lambda e lambda y, d squared f dy squared equals lambda squared e lambda y. You just bring down a lambda each derivative. All right, so you plug this stuff in, you have e iwt. Oh yeah, you can also cancel this stuff out, the e to the iwt. That helps out a lot. So then you have lambda squared e lambda y. Yep, minus density over mu iw e to the lambda y, because you just plug it in right there. Equals 0. Okay. Very cool. So now you can cancel those two out, and you solve for lambda, and you get lambda equals plus minus square root. It would be a plus minus I square root. Would it? No, because this term isn't negative, even though there's an I in it. Well, interesting. Okay, well, all right. You move that stuff to the other side, and you get a plus minus root density I W over U. You get plus minus that. Yeah, okay, this is what I did. I'm smart. Which equals plus minus density I W, nope. W over U times separately root I. And what is root I? I don't know. I don't know why I wrote that actually. Hold up. I'm gonna just assume that that's good for now. So, all right, anyways, you learn in freaking advanced, what is it called? I forgot what the class is called, but it's basically advanced math, although all math is advanced. You learn that if you have a lambda equals, let me get my notes. Here we go. If lambda equals plus minus I root something, let's call it A, then your solution is in the form A cosine, I don't want to call this A, I want to call it, what do I want to call it? X. X is bad, but you get the idea. A, so this is an unknown constant that we have to solve for, times X, whatever our variable is. In this case, I think it's Y. Yeah, it is Y. XY plus B sine XY. And then we have two unknowns, and we have to solve for them. If it's in the form of plus minus root X without the I, then it's A hyperbolic cosine XY plus B hyperbolic sine of XY. So, okay, sine is, my brain is blinking now. I don't want to draw that there. Sine starts at 0, and it goes like that, or whatever, right? Cosine starts at 1, and it goes down. I don't, it does something like that. Anyways, the main part is sine of 0 is 0, and sine, or cosine of 0 is 1. But for hyperbolic stuff, it looks like, I think it's like that, and then like that. And this one is sine hyperbolic, and this one is cos hyperbolic. And cosine equals 1 at 0. So same exact thing. Cosine hyperbolic of 0 is 1. And sine hyperbolic of 0 is 0. So that's all you need to know. So it performs the exact same. Cosine of 0 is 0, and cosine hyperbolic is 0. No, I said that backwards. Cosine of 0 is 1, and cosine hyperbolic of 0 is also 1. And same with sine, they're both 0. And then if you have a lambda equals just two separate numbers like A and B, then you'll get A this a and this a are different, but it doesn't really matter here. E a y plus b e b y. Technically, you get this form no matter which of these three cases you get, but you can use some weird Euler whatever math to rewrite this or as this, depending, like if you have I in there or if you have a plus minus, or I don't know, man. It's just, I have this written on my equation sheet, so it's pretty important. That's pretty important. But anyways, we have, which case do we have? We have this case. We have the second case because there's no I and it is a plus minus. So our solution is going to be in the form of f of y. Make sure I get this part right. Yep, I'm getting it right. Equals a cosine hyperbolic of lambda y b sine h lambda y. I'm going to keep it as lambda because I don't want to rewrite this whole thing each time. Technically, it's not the same lambda because this lambda is plus minus. This is technically, both of these could technically either be plus or minus, but I'm going to assume that they're plus and just not worry about it. Okay, so that's that. And we know that we substituted that in earlier. So now we have u equals EIWT FY, which equals EIWT, it's omega, but I like to call it W. A cos hyperbolic of lambda y plus b sine hyperbolic lambda y. That is correct. Okay. I don't know how long this recording has been going, but we're about halfway done. But it's all simple stuff. It's all simple stuff. I'm just going slow to make sure we get through all the extra steps. I'm going to leave this boxed so I don't confuse myself. Okay. Now, this is U homogeneous as a function of y and t, because we have y and we have t. Now, particular. Yeah, okay, this is interesting. I'm still grasping the understanding for this, but it's pretty neat. So now you rewrite the whole thing just as it is up here. That is d squared u dy squared minus, yep, density u du dt equals g over that cosine wt. Cool. And what did we say it had to be a function of? It had to be a function of t because t is on the right side. So let's assume u particular of t equals, here it gets clever, a cosine wt plus b sine wt. Now, you're probably asking, well, I asked, well, there should be a term that is a function of y in there also, but no, we don't need it because this right-hand side is only a function of t. So we can rewrite it like this. And that means du dy equals 0. And d squared u dy squared equals 0. And du dt equals wa negative wa sine wt. Yeah, okay, I can go out more. Plus wb cosine wt. Now we plug this in, and we get density u. I'm gonna write smaller. And I'm gonna bring in this negative sign when I write this. That is a minus. Oh, dang it, I wrote so big. But this equals g over that cosine wt. It's literally just rewriting this equation. That's it. Okay. So based on this, all right, I'm gonna multiply this in, and I'll do that. Dang it, I don't want to rewrite it. I'm not gonna rewrite it. I'm gonna have to suffer. There you go. Right, and then negative signs are there and everything. Probably. Okay, so this is saying there's a sign. Oh. This is saying that there is a sine, there's a cosine, and there's a cosine. So, A has to equal 0 because it's the only thing that's multiplying sine. And there's no sine on the right-hand side, there's only a cosine. So A has to equal 0. B, oh man, that's an ugly B. It's not as simple, but it's still pretty simple. So we rewrite what we have left, which is negative density WB over mu cosine WT equals G over mu cos WT. We cancel out those, It's an arrow, it's supposed to be an arrow. Negative, I don't even need to write it high. I'm solving for B. Is that similar to what I got in the notes? Yeah. Okay. Cool. So now let's rewrite U particular. So we said A is 0 and B is this thing. So it's negative G over BW sine. It's messy. Sine of WT. Cool. So the way homogeneous and particular stuff works is now you literally just add them to get the final solution. So U equals UP, well, I'm gonna write it in order. h plus up. Doesn't matter what order you write it, but I want to do it this way. And this equals e iwt a cosine lambda y, and lambda equals this thing. And it's a number. It's a number, probably. There's an I in there. I don't really know what to do with that, but I don't really care. B sine h lambda y minus g over pw sine wt. Is that what I have? That is exactly what I have. Okay, cool. Why aren't you letting me go down? Load more. There's no way. There's no way that's it. Dang it, I have to write super small now. Okay. Now we apply our boundary conditions. And what were our boundary conditions? Where were they? Up here. U at y equals 0 equals 0. U at y equals h equals 0. And that works because we have two unknowns. We have A and we have B. We originally had 4 unknowns, and these two are also called A and B. Maybe I should have called them C and D. But we were able to solve those two here and here. But we have these two left, so we have to use our boundary conditions. So U at y equals 0 equals 0. And this would be a beefy equation. Well, okay, if we plug in 0 into cosine, we get 1. Plug in 0 into sine, we get 0. So we're going to have A, and the second thing will go away, so just A. I'm going to write it nicer. A e to the iwt minus g over density w sine wt. So this is our first equation to solve for the unknown, and we can do it. It's not that bad. G wt over e iwt. There you go. That's the first equation. That's what A equals. And now we have the second equation, U y equals h equals 0. Yeah, there's no nice way to do this. That equals E iwt A cosine, and we'll plug in A, but I don't want to do it. Lambda h plus B sine. Are these hyperbolic? They are, aren't they? There's no escaping. I forgot to write a h there. These are hyperbolics. There's a lot of h's. Lambda h minus, oh dang, minus g over pw, density w, density omega, sine wt. This is the second equation. Now we have two equations, two unknowns, and you can solve for A and B, and then you'll have your answer, because you just plug A and B into this equation, and that's it. And then you can do some weird MATLAB plotting with it and get an actual solution, but like no one cares about that. Well, some people do. I don't. I'm done here. But yeah, that is about it. This is literally the hardest, in terms of highest level math, Navier-Stokes problem that you can do by hand. Next, I think I'm going to do a radial one, but I'll make it like a simple-ish radial one with radial coordinates. And then I'll do a little bit of CFD programming. But yeah, that's it.